So before lunch, we started dealing with the various trig derivatives. We dealt with most of the derivative of secant, but we have a little bit more we need to do over here. Let's see. Yes, very, very good. Oh my gosh. Oh, you're here. You're in the, yes, you're in the right place. Yes. I don't. Yes, you go do that. I don't know. Okay. So, this should become sine x over cosine squared x, yes? Right. To simplify this, I'm actually going to write the bottom as cosine x times cosine x because I can do a little bit of work with this. And I'll write the top as 1 times sine x. What's 1 over the cosine of x? No. 1 over the cosine of x. Secant of x. And what's sine x over cosine x? Tangent x. And hat off, please. Really shouldn't have to say that every day. So, the derivative of the secant of x is the secant of x times the tangent of x. The derivative of the secant of x is the secant of x times the tangent of x. We are not going to go through the proof of the derivative of the cosecant of x, but I think we can guess what it's going to be. First of all, actually, I'll let you guys keep writing. Hold on. We're going to do it in small pieces. First of all, each of these derivatives, they kind of come in pairs. Sine and cosine sort of go together. Tangent and cotangent kind of go together. Similar ideas. There's something squared. One's positive, one's negative. Secant and cosecant are going to go together. Do you think the answer is positive or negative? Negative. Seems like all the co-derivatives are negative. Instead of secant x, what do you think it's going to be? Cosecant of x. And instead of tangent x, what do you think it's going to be?
Cotangent x.
That is our derivative of the cosecant of x. I feel like when you memorize them, if you kind of memorize them in pairs, I know sine and cosine go together, I know tangent and cotangent go together, I know secant and cosecant go together and have similar structures and things. I think it kind of cuts down the, instead of 6 things to memorize, you only have 3 things to memorize. What I'm going to do right now is I'm going to pass out some index cards. So you can all write the 6 formulas on there. And then kind of keep these with you and do some memorizing, because we will need to have these memorized. No, you cannot use these on a quiz or on the test, but you can use these to prepare for a quiz or for a test. And when you write them on here, I would suggest writing them in pairs, taking up 3 lines instead of 6 lines. So you can have sine and cosine on the same line, tangent and cotangent on the same line, secant and cosecant on the same line. So you kind of see the similarities, and then don't have to memorize 6 things, only 3. While you are doing this, while you're writing things on the index cards, I'm going to pass around colored pencils. I went to Walmart. I've got all sorts of new colored pencils now, so, well, they're not the yellow and brown ones that we were left with. Take 3 colors. For our next quiz, which I think looks like I don't remember when it is, if it's Friday or next week or whatever, it's correct on your calendar. You will need to know the trig derivatives. I'll probably just ask you, tell me the derivative of tangent x, tell me the derivative of secant x, and you'll just memorization stuff. And really, these are just going to keep showing up all year long, so we do need to do some memorizing. When you are done with the index cards, I would like you to take a moment and find the derivative of this thing, which to me looks like I need to do some product rule stuff. Part of the product rule involves using the derivative of cosecant x, but now we know that, so you can handle that. Try that one, and actually when you're done, I'll give you another one to try as well. Your card looks just like what I have on the top. If you write down the formulas wrong, that's really going to be a problem if you're using this card to memorize things. Derivatives of all the co-functions are negative. And when you're done, please try the derivatives of those two functions that you see on the screen. X cosecant x minus cotangent x. And then f of x equals tan x over 1 plus tan x. And we should be quickly finishing up these two derivatives. I think there's product rule involved with the first and quotient rule with the second. Bless you. There's not too much simplifying we can do with the first one. I guess we could factor something out if we wanted to. I'm not going to bother. I'm getting negative x cosecant x cotangent x plus the cosecant of x minus the cosecant squared of x. I used product rule on that x times cosecant x thing. First, x times derivative of the second, derivative of cosecant x. That's one of our new trig derivatives. That's negative cosecant x cotangent x. Plus second cosecant x times derivative of the first is times 1. Minus, what's the derivative of cotangent x? Well, that's not right. What did I do wrong? Minus negative cosecant squared x, so we should have a plus cosecant squared x at the end. Take a moment, finish up that second one. I actually think this one should get cleaned up kind of nicely. secant squared x. Secant squared x over 1 plus tan x in parentheses squared, I believe. Is anyone getting that? Okay, a few people maybe. Basically, we now just have a few more things we can add into our product rule and quotient rule. I can make you do derivatives of these trig functions, which now are just things that we know. Still going? Anyone still going with this? Okay, so the next kind of random topic to look at that really doesn't have too much to do with product rule and quotient rule, but it's in the section of the book, so we might as well deal with this now, is the idea of what are called higher order derivatives. Higher order derivatives. And we will get to the colored pencils very soon. 3. Okay, you got like 2 minutes to finish that before we need things. Here's the deal. So, no, I really do need to be able to do this, though. So here's the deal. All the derivatives we've found so far, we haven't called them this, but they have been examples of what we call first derivatives. The slope of our original function, the rate of change of our original function, we have just found first derivatives. And we have a bunch of symbols for those things. Things like y prime, f prime of x, that dy dx thing, that operator notation d dx, find the derivative of f of x. We've seen all this notation. We've just been dealing with first derivatives. But there are other types of derivatives. For example, there are second derivatives. A second derivative is really just the derivative of a first derivative. It is the derivative of a first derivative. And I can show this by doing y double prime. That means the second derivative. F double prime of x. This one gets a little weird. D squared y dx squared. You square the d on the top, you square the x on the bottom. It's just the symbol. More with this symbol in the next unit, but I guess we're not squaring the d's in both because then it would look like we could cancel them, and that's not the case. For d dx squared of f of x. To find a second derivative, we'll calculate our first derivative and then find the derivative of that. We'll do this in a moment. But there's nothing that says we have to stop with second derivatives. Third derivatives. The third derivative is the derivative of the second derivative. Our symbols, y triple prime, f triple prime of x, d cubed y dx cubed, d dx cubed of f of x, and I am going to go one more layer because the symbols actually change a little bit after the third derivative, so I do want to show you the symbols for the fourth derivative, which is the same as anything beyond that. Because after like 3 tick marks, it's really tough to be able to look at a symbol and immediately tell how many tick marks there are. We changed the notation after this to say y with a little 4 in parentheses, kind of like a power, but it's not. It means the fourth derivative. Similarly, f with a little 4 in parentheses does have to be in parentheses to show it's a derivative rather than a power. Everything else is the same though. d4y dx4 d dx to the fourth of f of x. For example, let's say f of x equals x to the fifth minus 4x cubed plus 1, and we want to find Let's find the fourth derivative of this function. F of x equals x to the fifth minus 4x cubed plus 1. We want to find the fourth derivative. And can we do that right away? Can I go straight from the original to the fourth derivative? What do you need to get the fourth derivative? The first, and then the second, and then the third. So we have to calculate all these things. These are not going to be super hard, though. The first derivative, f prime of x equals, you know this. Plus 0 because it's constant. Perfect. Well, now I want to find the second derivative, which is just the derivative of the first derivative. What's the derivative of 5x to the fourth minus 12x squared? It's really like we're now just treating the first derivative as our original function, and I'm finding the derivative of that. Keep going. Find the third derivative, find the fourth derivative. Question, Lily. Okay. Tell me when you're not. With power rule stuff, I guess, but so many things we're going to deal with throughout the year aren't just power rule things. So no. Good news is you don't have to find too many fourth derivatives in the real world. It's mostly just first and second ones for things. Hopefully we can get 120x for our fourth derivative. For any polynomial, if you go far enough, what will the derivative eventually be? 0, because eventually everything becomes a constant, and then the derivative of that, but okay. We're not going to do one of these right now, but in the homework, they might ask you to find the seventh derivative of something and not give you the original, but give you like the fifth derivative. Would you be able to go from the fifth to this? That's why we're not going to do that right now. No big deal. I want to go back to particle motion very quickly. We're not going to do any problems. I just want to add something here. Let's put that away. Thank you. Particle motion. Oh my goodness. We said that s of t is our position function. And our velocity comes from doing the derivative of position. That's everything we've already done, because velocity is the rate of change of position. Robbie, what's the rate of change of velocity? Okay, and what is that physics-ish stuff? I'm looking for a word that means that's what I'm going for right now. The acceleration, it is the rate of change of our velocity. It's the derivative, stop. It's the derivative of our velocity. But, as Robbie said, we can also consider it to be the second derivative of our position, and that's acceleration. And we're not going to do anything more with this right now. You'll see something in the homework that asks you, find the acceleration at this time, or find the velocity when this is the acceleration. Same stuff as before, we just have another function we can work with now. That's all that we need to be able to deal with particle motion. There's a lot more to particle motion, but not yet. Position, its derivative is velocity, its derivative is acceleration. Okay, next thing that I want to do, which will involve those color pencils. Has everyone got mechanics colored pencils? Okay. Okay. So, next thing we need to be able to do, kind of switching over to dealing with things graphically, is we need to be able to look at a graph. There are two different things on this graph, and later there are going to be three things on this graph, and we need to decide which is f and which is f prime. Here's what I'd like you to do with the colored pencils. Because I feel like it gets a little bit complicated trying to look at all these graphs and sort of separate them, all we're going to do with the colored pencils is just trace out the entire graph so I clearly see this is one thing and the other is something else. So I'm going to trace this one out. I'm not doing any of the stuff I did before with positive slopes, negative slopes, and values. I'm just tracing the entire thing out just to help me kind of separate them. And you might as well go do the same in number 2. And here's the deal. One of these graphs is our original function, and the other is the derivative. Not sure which is which, but I know that where the original has a positive slope, the derivative has positive y values. Where the original has a negative slope, the derivative has negative y values. Looking at number 1, the way we're going to do this is we're just going to guess which is the original, and then see if the other actually kind of agrees with those slope ideas. So orange, purple, Elizabeth, guess which one is the original. There's no wrong answer. Why not? I'm going to call the original f. So now here's what we're looking for. F, what we're saying is f, has a positive slope until about here. Does the other graph have positive y values until there? Okay, so I think this is sounding good. But then I have a negative slope. Does the other graph have negative y values in that same region? And then so on. And yeah, everything is checking. So yeah, that was a good guess. F and f prime. There is a cheating way you could do number 1. Is that a hand, Daphne?
Sure, this is the way I do it. The orange one is like x cubed.
Yeah, doesn't the orange kind of look like a graph of x cubed? And you know the derivative of a cube is a square, so that works as well. However, the problem with that logic is how are you going to use that in number 2? That's the problem. Absolutely, I wanted you to see that cheating method for number 1. But for 2, there's no way around it. Let's just guess and then see if slopes on one match with y values on the other. So, Marissa Drozik, just guess. Orange or purple, what do you want to call f?
Okay.
Why not? Okay, I see a negative slope until about here. Does the other graph have negative y values there?
No.
Okay, then I see a positive slope. Does the other graph have positive y values in that same region? I think that's good. Then I see a negative slope. Everything is working here. That was a good guess. Maybe it wasn't so much of a guess. No, maybe she was just like thinking through things and not guessing. Or maybe she just guessed, I don't know. Yeah, 50-50 chance. Okay, do we see how this works? This gets more complicated when we throw a third graph on there. That's why you have 3 colors. I want you to go and trace out the 3 things, and then together I want to go through the logic with you guys. Then hopefully we'll have time for you to try one totally on your own. But right now, just trace. While you're doing this, I'm going to pass out the homework. Because of the holiday, I'm not supposed to give you homework on Tuesday night. So if the holiday is an issue, deal with things tonight. Yeah, it's not over with. This is also why the quiz wasn't Thursday, though. Which is what the website apparently said. Oh. And I think at the end of the period, I'm going to leave the can of colored pencils over here. You're going to leave things in there. Okay, here we go. We are just going to guess which one is F. Josh, just guess. What's F? I shouldn't have asked you. I'm sorry. Sorry. Trey. I'm sorry. I apologize. The top one. Perfect. I'm going to call that f. Who knows? Let's see. I want to do it over here so people watching can do things. I have a positive slope. Do I have a graph with positive y values until there?
Yeah.
Which? Orange. Okay. So let me see if things continue to work. I see a negative slope. Does orange have negative y values between here and here? Oh. Hello? That's okay. Rachel, yes. Yep, bye. You're getting dismissed. We've got to finish this one. Please listen. Please listen. I see a negative slope here. Does orange have negative y values there? Yes. Positive slope. I see positive y values. Now, I do not actually know if purple is f and orange is f prime. But I do know that orange is the derivative of purple, which really means it could be f and f prime, or maybe it's f prime and f double prime. I don't really know what order they go in, but I do know that orange is the derivative of purple. Let's see if green is the second derivative, which means I'm going to look at the orange graph and see if its slopes get matched up with the y values on green. I see a negative slope until here. Does green have negative y values until there? Yeah, it does. Then I see a positive slope. I see positive y values. Things are checking. Negative slope. Negative y values. Oh, it shouldn't have been traced over there like that. I'm not sure what I was doing with that, but I think this is the order we should go in. Just guess. Then see if the slopes on the first match with y values on something else. If so, that second one is the derivative of what you started with. And then try to go on to the third and see is that the derivative of what you just dealt with, or maybe that's the original and you'll readjust. On your way out. Actually, let me stop this.